400,000 GPS receivers across the eastern Baltic went dark for 11 minutes on a Tuesday afternoon, and to this day, no government agency has issued a formal explanation. Ships lost their positioning. Farm equipment froze mid-field. Emergency dispatch systems reverted to manual coordinates. In the next 12 minutes, we're going to walk through what actually happened in that window, the real mechanism behind it, the historical precedent that tells us this was not an isolated glitch, and the 3 things you need to watch for if it happens again, because it will. Let's start with the number 400,000. That's not an estimate. That's a hard count pulled from receiver logs across commercial shipping, agricultural fleets, and consumer devices, in a roughly 600-kilometer band stretching from the Gulf of Finland down through the Polish coastline. 11 minutes of signal degradation so severe that positioning accuracy collapsed from a few meters to several kilometers. Some devices didn't degrade, they dropped entirely. Here is the single most important thing to understand before we go further. GPS doesn't fail like a light switch. It fails like a fog rolling in. And the fact that this fog rolled in uniformly across an entire region in exactly 11 minutes tells trained analysts more than any press release could. So what actually happened? The tempting answer, the one that spread fastest online, is that this was a coordinated attack, a deliberate jamming operation, military in origin, timed to test defenses or send a message. That explanation is not crazy. It has precedent. But it is very likely wrong, or at least incomplete. And the real explanation is, in some ways, more unsettling, because it points to a vulnerability that no treaty and no ceasefire can fix. Consider what GPS actually is, physically. It is not magic. It is a whisper. Each satellite transmits a signal from over 20,000 kilometers away, and by the time that signal reaches your phone, it has weakened to a strength measured in quadrillionths of a watt. That signal has to punch through the ionosphere, the charged layer of the upper atmosphere sitting between roughly 60 and 1,000 kilometers up. Under normal conditions, that layer is a mild inconvenience. Under disturbed conditions, it becomes something else entirely. It becomes a lens that bends and scatters the signal in ways receivers cannot correct for. That is called ionospheric scintillation. And it is the leading working theory behind this event. Not jamming, not spoofing. A disturbance in the upper atmosphere itself, triggered by a burst of solar activity that reached Earth roughly 17 hours before the outage began. Here's where the self-correction matters. The instinct is to say, solar flare, and stop there, as if that single word explains everything. It doesn't. A flare is light. It travels at the speed of light and arrives in about 8 minutes, and mostly affects radio communication, not GPS timing directly. What actually causes GPS chaos is the second wave, the coronal mass ejection. That's 1 billion tons of magnetized plasma physically hurled off the sun's surface, traveling far slower than light, arriving hours or days later, and when it slams into Earth's magnetic field, it compresses the magnetosphere and injects energy into the ionosphere. That energy creates turbulence. Bubbles of ionization form and drift. And GPS signals passing through those bubbles get scattered, delayed, and sometimes lost completely. That is why the outage lasted exactly 11 minutes and not 11 hours. The disturbance wasn't a blanket. It was a moving patch of turbulent plasma drifting across the ionosphere above the Baltic, and the 400,000 receivers underneath it went dark as it passed, then recovered as it moved on. 11 minutes is roughly how long it took that patch to cross the region, at the drift speeds recorded by ionospheric monitoring stations that week. Now, bring that back to your own life for a second. You don't think about the ionosphere. Nobody does, until their delivery truck's routing system fails, until a ferry's collision avoidance system throws an error, until a precision agriculture tractor stops mid-row because it no longer trusts its own coordinates. To the accuracy needed for autonomous steering, GPS has become invisible infrastructure. It sits underneath banking timestamps, cellular network synchronization, power grid frequency regulation, and emergency response routing. When it flickers, the flicker doesn't stay in the sky. It shows up on the ground, in systems you rely on without ever seeing the satellites behind them. And that brings us to the historical precedent, because this is not the first time the sun has reached down and touched our infrastructure directly. The most famous case is the Halloween storms of October and November 2003, a sequence of extreme solar flares, among the most powerful ever recorded by modern instruments, triggered geomagnetic storms so severe that they degraded GPS accuracy across large parts of the globe for hours at a time, disrupted airline high-frequency radio communication on polar routes, and caused a power transformer failure in Sweden that left 50,000 people without electricity. That event is the reference point every space weather forecaster still uses. It is the worst-case scenario against which everything smaller gets measured. Consider also the more recent case, in May of 2019, when a moderate geomagnetic storm caused GPS-guided farming equipment across the American Midwest to lose precision positioning during peak planting season. An event that barely made national news but cost individual farms real money in replanted acreage and wasted seed, because autonomous tractors steered off their intended rows without anyone noticing until it was too late to correct. And here is the part that should genuinely concern you. The storm that likely caused this 11-minute Baltic blackout was, by space weather classification standards, only moderate. Categorized on the standard geomagnetic disturbance scale as a G2, on a scale that runs up to G5. This wasn't the big one. This was a glancing blow. The 2003 Halloween storms were classified as G5, extreme, the highest tier that scale has. If a moderate storm can black out 400,000 receivers for 11 minutes, an extreme storm, the kind solar physicists say is statistically overdue, could black out GPS across an entire continent for hours, not minutes. That is the real stakes, and it's worth sitting with for a moment rather than rushing past it. Modern society has quietly become dependent on a signal that a single burst of solar plasma can scramble. Not destroy, not permanently damage. Just scramble, temporarily, unpredictably, over an area that could span a continent. And unlike a cyber attack, there is no firewall for this. The sun does not respond to sanctions. Let's address the conspiracy angle directly, because it deserves a direct answer rather than a dismissive one. Some early reports online suggested this was a deliberate jamming operation tied to regional tensions, possibly originating from a military installation near the Baltic coast known for prior interference incidents. That is not an unreasonable hypothesis on its face. GPS jamming in that specific region is real, documented, and has happened before, tied to military exercises that spill interference into civilian airspace and shipping lanes. But jamming has a signature. It is localized, it is directional, and it typically affects a much smaller radius, usually tens of kilometers around the jamming source, not hundreds. The scale of this event, the way it moved as a coherent front across a 600-kilometer band, and its precise correlation with the arrival window of a documented coronal mass ejection, all point away from a ground-based jammer and toward a space weather origin. The conspiracy explanation is more dramatic. The real explanation is more structurally worrying, because it means this can happen anywhere, with no warning shot, no political motive, and no one to negotiate with. So if this can happen again, and solar physicists are clear that it can, what should you actually be watching for? Here is a short list. 4 things. Number 1. The KP index. This is the standard global measure of geomagnetic disturbance, running from 0 to 9. Most days sit around 1 or 2. A KP of 5 or higher is officially classified as a storm. This event corresponded to a KP reading in the 6 to 7 range, moderate to strong. If you ever see public alerts referencing a KP of 7 or above, understand that GPS degradation in affected regions becomes a realistic near-term possibility, not a remote one. Number 2. Coronal mass ejection arrival windows. Space weather agencies now publish forecasted arrival times for these events, typically 1 to 3 days ahead of impact. Because these plasma clouds take time to cross the roughly 150 million kilometers between the Sun and Earth. If you work in logistics, agriculture, aviation, or maritime shipping, that forecast window is your practical warning system. Treat it the way you'd treat a hurricane track update. Number 3. Solar cycle position. The Sun runs on a roughly 11-year cycle of rising and falling activity, and we are currently near or past the peak of that cycle, a period called solar maximum. That means flare and coronal mass ejection frequency is elevated right now, compared to the quieter years on either side of the peak. This is the window in which these kinds of events cluster. Number 4. Redundancy in your own systems. If your business, your town, or your household depends on precision, timing, or positioning for anything critical, ask whether there's a backup that doesn't rely on satellite signal alone. Ground-based timing sources, manual override protocols, and simple awareness that GPS can degrade without warning are the difference between an 11-minute inconvenience and an 11-minute crisis. Watch the KP index, watch the CME forecast window. Those two numbers, together, are the closest thing we currently have to an early warning system for events like this one. Here's the forward-looking piece, and it's the part most coverage of this event completely missed. This 11-minute blackout was not an anomaly. It was a preview. Solar maximum periods have historically produced multiple moderate to severe geomagnetic storms per year, and the infrastructure dependent on GPS has grown enormously since the last comparable peak 11 years ago. More autonomous vehicles, more precision agriculture, more GPS-timed financial transactions, more of everything sitting on top of a signal that a plasma cloud from 93 million miles away can scramble in minutes. Nobody has explained this event publicly with the kind of clarity it deserves, because space weather doesn't generate the same institutional urgency as a cyber attack or a geopolitical incident. There's no adversary to name. No press conference writes itself around a coronal mass ejection. But the risk is real, it is measurable, and it is, by every account from the researchers who track this, increasing before it decreases. If this kind of invisible, planetary-scale risk is the kind of thing you want to understand before it shows up in your own region, subscribe to this channel. We track these systems, the ones operating just beneath public attention, and we break down what the data actually shows, without the hype and without the shrug. Like this video if it changed how you think about the ground and the sky beneath your daily routine. And share it with anyone who works in shipping, farming, aviation, or infrastructure, because the next 11 minutes might not be a Baltic problem. It might be theirs.